Okay, AB number 4, worksheet 1210. This is another multiple choice packet, and we're going to focus on some topics that we haven't talked about yet. But we're going to talk about integrals and techniques for integrating substitution, integrating by substitution, which is a very common way of dealing with reverse chain rule, fundamental theorem of calculus. And so the intention is you haven't really even tried these yet, but there will be points during this video that you should pause it, try a problem or 2 or 3 or whatever I ask you guys, and then unpause it and see how you do. So just some notes up here. So these handouts are kind of little mini lessons also, review lessons. U-Substitution is the reverse chain rule. Now, the chain rule for derivatives gets used all the time, so we can expect that we have to reverse it quite a bit. Now, this is sort of a generic way of writing it, which I don't really think is like something you should memorize. It's more of a method, but this sort of just illustrates the idea that you're going to have the derivative of something in an integral that you're trying to undo, and it might have its own function inside, but then you would hope to see the derivative of what's outside of it because of the chain rule. If we had taken the derivative of that, we would get this extra g prime, and hopefully it's there. Now, if that is the case, that you see an inner function whose derivative is there, then the final answer would just be f of g of x plus c. So that's sort of just a kind of a generic way of writing U-Substitution, but fundamental theorem of calculus, FTC, part 1. There's 2 parts. Part 1 says that if you integrate a derivative, you will get the original function. We kind of use this idea to undo derivatives, solve differential equations, but a lot of times we use this with definite integrals where we have values, and if that's the case, then we get f of b minus f of a, and it gives you the change. What this represents is, the total change in f of x from x equals a to x equals b, and this is often used on word problems for response problems to talk about, we're integrating derivative velocity. That's the change in position, right? Because anyways. FTC part 2, we don't use as much, but we do use it quite a bit, and that's when you take the derivative of an integral. So it's the other way around, and so there's a function side here. Now, usually we use different variables inside than what are in the limits, because the limits are usually going to have x's in them. And so the most proper way is to put a different variable on the inside. I'll admit I'm often lazy, and I just put the same variable in there, even though it's not technically correct. So you might want to watch out for that on free response, kind of specifically like rate models. Anyways, when you do this, the derivative undoes the integral, but then you have to plug the limits inside of the function and subtract, and you got to plug the bottom one into the function. But there's this extra layer of the derivative that hasn't been finished yet. So we've undone the integral, but the limits, they didn't have their derivatives taken. They ended up inside. So chain rule says we have to multiply by what we plugged in afterwards. And that's something that people forget to do. And if it's just a number, then the derivative of the number is just going to be 0. It's going to drop out. So that's part 2. So quick little notes there. Why don't you guys try right now 2, 3, and 5. So why don't you guys try 2, 3, and 5? Pause the video and try 2, 3, and 5. And then after you've tried them, unpause it, and we will go over those problems. Okay, so hopefully you tried these. These are, this is a pretty basic integration, just to remember how to do it. It's power rule, bump it up 1, divide by the new exponent, plus 3x. We don't need to write the plus c because it's a definite integral. So we're going to plug 2 in And that's going to be 16 over 2 plus 6 minus 0 plus 0. And so that's going to be 8 plus 6 is 14. Okay. Let's look at number 3. 3 says, for what value of k being positive, does this integral equal k squared? So this reminds me of some of the problems we've been doing recently with like, find the value y equals k that splits the area in half, or, you know, those kind of problems. So it's kind of like that, but it's already set up for you. K is just a number. So we're going to integrate this. It's going to be x squared over 2 minus 5kx, because 5k is just a number. It's a definite integral. And then we're going to plug limits in. So k gets plugged in first, and that's going to give you 2k cubed minus 5k squared minus 0. Be careful. When you plug 0 in, sometimes it doesn't give you 0. So I just always kind of make sure I think about it. And now we got to solve this. So this looks like, now I'm going to treat this like a polynomial where I'm trying to solve for k. So we get 2k cubed minus 6k squared equals 0. Move everything one side, factor out the GCF. And we get k equals 0 and k equals 3. Now 0 isn't in the list, but they told you also that k has to be positive. So there's your answer. Doesn't that kind of remind you guys of those problems we've done in some recent tests? Number 5 is just indefinite integral. It doesn't have any limit, so you're just trying to find the antiderivative plus c. So it's going to be 3x. Hold on. How do we do with that squared? Now you can square this. You could FOIL this all out. 3x plus 5 times 3x plus 5, and then integrate what you get after that. But this is a chance to use U-Substitution. U equals the inner function, du equals the derivative of the inner function, 3 dx. We don't see an extra 3 there that we want, so we're going to get rid of it. So what we're trying to do is rewrite this into terms of all u and du stuff. So the dx gets replaced with the 1/3 du. I'm going to put the 1/3 out in front. And it's going to be u squared du. And they're going to get u cubed over 3 plus c. And then you're going to get 1/9. And we're going to replace, you got to replace u back with x. 3x plus 5 cubed plus c. So that would be answer D. So little U-Substitution review. All right, let's go to the next page. You guys are going to get to finish those problems after this on your own. Check your answers. So we're doing about half the problems together. Let's see. I want you guys to try. Try 7, 8, 10, and 11. So maybe just try 7 and 8 for a second. Pause it. After you do 7 and 8, we'll do it. And we'll pause again and do the next two. Just kind of break it up a little more. So try 7 and 8 on your own. Pause the video. Okay, so this might make you think of inverse tangent. Hopefully it does make you think of inverse tangent, but it's not inverse tangent. This is U-Substitution equals x squared plus 1. Du equals 2x dx. We wanted x dx. That's good. We don't want the 2 though. And so we're going to rewrite this as the integral. We're going to put a 1/2 in front, and it's going to be du over u. Now, sometimes on multiple choice, they like to give you answers that aren't integrated, that are like this with the u's. And if you do that, you got to make sure you change your limits to the u limits. These are x values. So when x equals 3, u would be 10. When x equals 1, u would be 2. And so it would be 2 to 10 if you're going to leave in terms of u. Also, you could use this technique if you like. The antiderivative 1 over u is natural log of the absolute value of u. This is a definite integral. You could use these u limits to finish the problem and not change it back to x. Now, I don't really think that usually saves me a lot of work, so I just typically just change it back to x and use the original x limits. And so usually if I know I'm going to do that, I don't even bother writing the U limits on this step. I'm just like, whatever, I'm going to change it back to X. But sometimes you're forced to do this, change it to U limits when they give you answers that are choices like that. So natural log of absolute value of 10 minus 1/2 natural log the absolute value of 2. Now, they typically will simplify these answers using log rules. So there's a couple ways to deal with this. You could think of this as 1/2 natural log of 10 minus natural log of 2, because usually when you're going to combine these with, if it's subtraction, you're going to divide the first one by the second one. You don't want stuff in front. So this is 1/2 natural log of 5, and that is there. The other possibility is you could have brought the 1/2s inside as exponents, and then you'd have natural log of the square root of 10 minus natural log of the square root of 2, which would give you natural log of the square root of 5, which, by the way, is the same as this because we could bring this in here. You just need to be aware that they can kind of like mess things up. Now, number 8 is exactly that situation I was talking about. So they're actually telling you to use U-substitution, which is nice. That's probably what I would have done anyways, right? And so you got to finish keep doing the U-substitution. You get an x dx, which is good. We don't want the -2. So we're going to rewrite it as -1/2 integral of the square root of u du. Now, you get to stop. The problem is that people are going to put 0 and 3 here and choose answer C, but it's wrong because those are x limits. These are x limits. So if you're going to actually put an answer with all u's in it, it needs to officially have everything with u's in it. So if u equals 25 minus x squared, well, when x is 0, u equals 25. And when x equals 3, u is going to equal 16. So we're looking for the one that's 25 to 16, which you're like, oh, there it is. But it doesn't have the negative. Oh, well, that one's wrong too. Shoot. Well, there's a couple of 1625, but they're upside down. Can I just flip it? No, you can't just flip it, but you can flip it. You guys remember what happens if you flip the symbols, you get the negative of what you would usually get, and it's already negative, so it becomes positive. And that's what you have. Don't flip the 1/2 though. So that was kind of a tricky one. Just be aware of that. But they're going to put that answer with the x's on there, and you're going to feel really good about it. Try 10 and 11. If you haven't yet, try 10 and 11. Pause the video. Try 10 and 11. Okay, so the antiderivative of 2 tangent x. Okay, so we're trying to integrate 2 tangent x. They just word it differently. And it says for 0 to pi over 2, I don't know what, this isn't a definite integral, but we'll figure out what that means in a second. Do we know the rule that gives you tangent as a derivative? We don't. It doesn't exist. So we want to rewrite this as sine over cosine, and then use U-substitution, U equals cosine x. I mean, I know people here would say, oh, tangent, that's secant squared, right? Which is on here. Oh, don't pick that. Secant squared is, you're going the wrong way. You're taking derivative. Du equals negative sine x dx. We don't want the negative. So we're going to get this as -2, and it's going to be du over u. So it's going to be -2 natural log of the absolute value of u plus c. Well, the antiderivative is the part without the plus c. So it's interesting. Rewrite it back in terms with the original variable. And it's saying that it's 0 to pi over 2. Cosine curve from 0 to pi over 2 is this part, which is always positive, which means we could rewrite it without the absolute values. So, but that answer is not there. Oh, man. Okay. Log rules, we could bring this inside. There's a couple answers without anything in front. So we bring it inside as an exponent. Okay. And so then we could rewrite it as natural log of 1 over cosine squared, which is still not on the list, but you should also think, well, 1 over cosine is secant, and we get secant squared. So number 11, Now we have two choices for our u. Should it be secant? Because this is, I think sometimes I like to write it like this. This is secant squared. This is tangent squared, right? So it could be secant x as the inner function or tangent x as the inner function. Now, whichever one you pick for u, you should see the derivative of elsewhere. So here, du, derivative secant, is tangent, is secant tan. And while you might be like, well, I'm going to use one secant for my u and then the other secant and tan for my du, but then you have an extra tangent left over, so that's not going to work. Tangent, though, derivative tangent is secant squared. And so that's perfect because then we're going to rewrite this as u squared du. And that's going to be u cubed over 3 plus c. That's going to be 1/3 tangent x cubed plus c. So that is answer A. So sometimes you just don't be afraid to try different things for u's, and if they don't work, it should become obvious. And then your next step is to be like, well, is there a different thing I could try for u? And then, oh, it works. Okay, let's go to the next page. I want you guys to try 14 and 15 on your own first. Try 14 and 15 on your own first. Pause the video, and then we will go over those together. So pause it, try it. 14, your first thought is usually to pick the denominator or what's in the denominators of u. And I would say that usually works out nice. This doesn't work out because we don't have an x on the top. So that's not going to work. So then you start to think more creatively, like, well, is that some kind of special rule? Like that makes me kind of think of inverse sine. The integral of 1 over the square root of 1 minus x squared dx is inverse sine of x. The problem is that it's usually not going to be so nicely set up for that. We need a 1 here. So we got to force that to happen first. So we need to make this 1, we could divide a 4 out of it, but then we got to divide a 4 out of this. So I could rewrite this as 1 over 4 parentheses 1 minus x squared over 4. Then we could take the square root of 4 out as a 2, right? Put it out in front. And then now what we got to do is figure out, okay, well, we want this just to be something squared right here. So we got to say, well, what would you put in parentheses that you would square it and would give you x squared over 4? And be like, oh, that's x over 2. That's your u. U equals x over 2. Du equals 1/2 dx. I don't want the 1/2, so I got to multiply both sides by 2. Okay, and now I already have a 1/2 in front, but now I have a times 2 because of that. And then it's going to be du over the square root of 1 minus u squared. So that's going to give you inverse sine of u plus c, but then you got to rewrite it back in terms of the original variable. U is x over 2. So we're looking for inverse sine of x over 2 plus c. Now, inverse sine is also called arc sine sometimes. So those rules come up, and you usually have to kind of manipulate them. 15, if f and g are continuously differentiable functions for all real numbers, which of the following definite integrals is equal to f of g of 4 minus f of g of 2. So this looks like composite functions inside of the function. So we're probably looking for a chain rule where g is inside, and we're going to go 2 to 4. So they all have 2 to 4. So that's not really the issue. So the issue is which of these is going to give us f of g of x for the answer. So we're looking for a chain rule. So we see f prime of g of x, and the integral would undo the derivative, but then you have this inner function. So we need an extra g prime of x out here for u substitution, right? If u equals gx, then du equals g prime x dx. So we need a g prime x dx. This one has f, it needs to be g. This one just didn't have it. This one looks promising. Let's just check the others. Oh, nope, this one wasn't good because it needs a prime right there. This one has a prime. That looks good. This one has a prime on the inside instead of right here, so that one's bad. So it's D. So kind of interesting problem. Okay, next problems are going to be about some of the other properties of definite integrals. And so there's this idea that says if you have an integral from a to b of a function, and then you're adding it to another integral from b to c of that function, you can combine them together into a new function where, so these have to match this, and then what's on the bottom and what's on the top go to those spots. So we can combine integrals together, or you can use the same idea backwards and break up an integral, which sometimes we have to do. Okay, so why don't you guys try 17? And then, so pause the video, try 17. And so we have 2 to 8 and 2 to 4 and 8 to 4. So we know 2 to 8 and 8 to 4. Now we want to kind of like add these together so that we get 8 to 4. But there's a problem. They do have matching limits, but one needs to be in the bottom, one needs to be in the top. They're both on the bottom, so we're going to have to flip one of them and change its sign. And we specifically would like 8 in the bottom and 4 on the top. So let's leave this one the same and flip this one. So we could do 8 to 2 of f of x dx. And that's going to equal the negative of what it equaled before. So that's going to be positive 10. So then we're going to add that to 2 to 4 f of x dx, which equals 6. So we've got the matching ones, one on the bottom, one on the top. This is going to give you 8 to 4 fx dx by adding these. So it's always adding two of them together. So that's going to equal 10 plus 6 is 16, positive 16. So properties of definite integrals. Okay, moving on to the next page. Let's talk about absolute values briefly. So absolute values, if you have a graphing calculator, they're really easy because you can just do absolute value in your calculator and they'll integrate it for you. But the strategy, if you have to do it by hand, is to break it up when the sign changes from positive, negative, negative, positive, and then to fix the negative parts by forcing them to be positive. So we'll do one. You could try it ahead of time if you feel like you remember how to do it. Otherwise, you can watch these and then do the next one on your own. So you want to figure out, there's a couple ways to do this. One, you could graph this. You could use geometry because it's a linear absolute value, which is possible only if it's linear. Otherwise, because it gives you nice triangles and rectangles that you can find the area of. But usually what you're going to do is you're going to set this equal to 0 to find its x-intercepts. And then you might do like a line check and say, okay, well, it's at negative, it changes to -2. Let's test. This is the original function. This is a derivative test, like x equals 0, positive, negative. So we're going to break it up. So the first thing is we're going to do -3 to -2. And then we put parentheses. The whole point of this is to get rid of the absolute values. And then we're going to do -2 to 3 of the same thing. Now, we're breaking them up. The negative part has to be fixed by adding an extra negative in front of it. And then this one will stay positive because it's already positive. So now you're going to do the work. The antiderivative is going to be x squared over 2 plus 2x. Limits -3 to -2 plus the antiderivative is the same, x squared over 2 plus 2x, -2 to 3. And then we're just in for some busy work here, but be very careful. So when you plug -2 in, squared is 4 over 2 is 2 minus 4. Minus, when you plug -3 in, squared is positive 9 halves minus 6. plus this one's going to be 9/2 plus 6. And then minus -2 squared is positive 4/2 is 2 minus 4. So now we just got to carefully get through all this. So this is going to be -2. This is going to be -3/2, but then it gets made positive. So this is going to be -2 plus 1.5 is -1/2. Plus, so that's the part that we thought would come out negative, and it did, and we have an extra negative to fix it, so it becomes positive 1/2. This one should come out positive. This is -2. This is 21/2 plus 2. So that's 25/2 or 12.5. So this is 12.5. So we get 13 for our answer. On a graphing calculator, you just do math 9, F end, and then you go to the math menu again, go to num, absolute, ABS, and then your calculator will do it for you. You don't have to split it up. Okay, area. I'm going to jump down to area. Now, these ones we've been doing more recently, so I don't think, I think I'm going to let you probably try to do all these on your own, but just quick notes. If you want to find the area, you can do vertical slices, and the dimensions of your slice are going to be the top y coordinate minus the bottom y coordinate. And then the width of the slice is dx. It's like they're thin rectangles, and you're going to integrate from x left to x right. But you could also do horizontal slices. So these are vertical slices, and you could do horizontal slices. And horizontal slices, you'll get the same answer, but your slices will be sideways, and it'll be x right minus x left, and the thickness will be vertical dy, but then you won't want to integrate in the y direction from the bottom y coordinate to the top y coordinate. So that's how we do it. Now, we've been doing this a lot lately, so I'm kind of thinking I'm going to let you guys just try those next 4 problems on your own, check them, look at my work if you have trouble. Okay? So jumping down here to average value, and this is mean value theorem. There's a couple versions that we've learned. One version works all the time. The other version works for derivatives. So we'll do a quick little note thing here. So we'll start with the derivative one, mean value theorem. So mean value theorem. Mean value is average value. And we'll do it for derivatives first. And that was the first one I taught you. And so that's average slope. I would say that often on the AP test, they refer to it as average rate of change. All right. Derivatives are slope. Derivatives are rates of change, average rate of change of something. The idea is pretty simple. You have a curve. I'll just draw a picture to represent this. You have a curve, some function, fx, and you want to know, say, from some point A to some point B, what the average slope is. Well, there's an infinite number of little tangent line slopes that you're trying to average, right? So slopes are changing. You've got lots of different slopes, but it's simply the average is going to be the slope of the line. We call this a secant line. So we're trying to find the average of the tangent slopes, but the secant line is going to equal the average slope. So it's just a point connecting the endpoints of the part of the curve that you're trying to find the average of. So that's the idea. You're just trying to find the slope between the endpoints, and that's enough. Now, we could try and write a formula and stuff for it. I don't think it's worth trying to memorize it. We could say, well, this is AFA and this is BFB. And so the average slope of F or f prime average is going to be the rise over run, fb minus f of a over b minus a, rise over run. So that's for derivatives. Now there's this other part that says that whenever they talk about the guaranteed mean value theorem, there's this idea that the actual slope will equal the average slope at least once between the endpoints, and they usually refer to that as the C value, but that's the guarantee. And the way you find that is you find your average slope, then you find the derivative of your function, and you set them equal to each other, and you solve the equation to find out when that's true. Now, the other version of the mean value theorem is for just regular functions, which derivatives can be treated as regular functions, okay? But in this case, we're looking for the average y value of a curve. Now, I don't know if you guys remember the example I used in class of like a measuring cup with flour and it's all lumpy and you want to smooth it out. Well, the amount of flour that's inside after you kind of shake it down, level it out to make sure you have the right amount is the same amount as when it was all lumpy. And so what we're doing is we're going to take a function f of x, and we want to say, well, we want to find the average value of the function between point A and point B. So you need some endpoints. You say, well, I mean, you look at this, you'd be like, well, it kind of looks like it's probably somewhere around here, right? The average y value of all these y values. The way we're going to do it, though, is we're going to take this area underneath it. We're going to smooth it out so some of the high points will fill in the low points, and you'll get the same area, but now it looks like a rectangle, right? And the height of that rectangle is our average height. That smoothed out height is the average height, okay? So our strategy is to say, okay, well, if we know the area of this rectangle, we could divide it by its base, and then we would get the area. And the area of that rectangle is the area under the original curve, so we do know the area of the rectangle. So we're going to say, okay, well, area of the rectangle, we'll start with this. This is how we kind of derived it, and it's not too. The area of the rectangle equals base times height, right? And it equals also the area under the original curve that we smoothed out to get it, the integral of f of x from a to b. So if we want the height, this is what we want. The f average is the height. We have the base. The base is the right x coordinate minus the left x coordinate, b minus a. So we could just divide both sides by the base, and that would give us our average height. So f average equals 1 over b minus a, integral of a to b of f of x dx. I wouldn't memorize this because back when I tried, I would always like mix this up with like a fundamental theorem of calculus part 1 because it kind of looks like that, or whatever I could remember, which is b minus a or a minus b. If you use just this simple idea, it's a visual idea, you should get it right every time. Okay, now that is that, and there's also a guarantee that the actual y value will equal the average y value at some point, at least one time, and sometimes you're asked to find that, okay, or asked to use that idea to make a conclusion about something else. Now here's the interesting thing. If we use f prime average, because f prime is a function, so we could use this idea with it, we do 1 over a minus b minus a to b of f prime of x dx, and the antiderivative of f prime is f, and then we plug the limits in and we get f of b minus f of a over b minus a, which is the same thing we got before. Now you could do this every time you're dealing with derivative, but this is going to be faster because we're going to get to the same result with extra work. When you like to just do less extra work. Let's see if we could try one or two of these problems. None of them are asking for the. Let's try 26, and then we'll do another. Try 26. Pause the video. Try 26. Then I'll do it. So mean value theorem, closed interval. So you got to make sure you have a closed interval. It also has to be a continuous function. And this doesn't sound like the derivative, right? So I think we're going to do f average equals the integral of our function from -4 to 0, and then we're going to divide by the base, which is always the top limit minus the bottom limit. You should get a positive base. If you get a negative base, you did it wrong. Okay, so it's going to be 1/4. The antiderivative this, U-Substitution, you could do U-Substitution, or you could be like, okay, well, it's going to have a sine 1/2 x for sure. And then chain rule is going to give me an extra 1/2 in front, which I don't want, so I need a 2 to cancel it. Well, if you did U-Substitution, all that work would give you that extra 2. So that's up to you. All right. So we plug 0 in, which a lot of times your trig doesn't give you 0, minus 2 sine of -2. Okay, sine of 0 is 0. So I'm saying my answer is -1/2 sine of -2. But that answer is not on there. Well, there's some properties of sine and cosine. Cosine is called an even function, which means values on the right are exactly the same as values on the left, positive, negative. But sine is an odd function. You guys look at the graph here. If you plug in 2 and you plug in -2, you should get the same answer, but negative. So this is a property of sine that says you can do sine of +2 and just put an extra negative in front, and that will give you the value because it's an odd function. So then that gives you +1/2 sine of 2, which is on the list. So tricky. Okay, let's go to the next page, and why don't you guys try 29? Yeah, let's just try 29. I don't think it has to do with average value, but let's just try it. It looks interesting. Try 29, pause the video, and then we'll talk about how to do it. Okay, now, even though 29 isn't about average value, it's an issue that could come up in average value. Okay, so if you want to integrate some function and it's a piecewise function, or the function changes from one part to another, you're still, for average value, going to want to find the whole area and divide by the whole base. You're not going to want to have to do individual areas by individual bases and get individual average values that you add together. That's not going to be the right answer. So this is a piecewise function. So the main idea here is to find the area under this whole curve, or to integrate this whole curve. We are going to have to break it up. So we're going to have to do -2 to 0 of x fx dx plus 0 to 1 of fx dx separately. Right? Okay. Now, from -2 to 0, we're going to go ahead and plug what fx is for that part. And from 0 to 1, we're going to plug in x plus 1 in parentheses. So now we can integrate these separately. This is going to be -2 to 0 of x squared dx plus 0 to 1 of x squared plus x dx. Distribute that. So the antiderivative here is going to be x cubed over 3, -2 to 0, plus x cubed over 3, plus x squared over 2, from 0 to 1. So we're going to plug 0 in and get 0 cubed over 3 minus -2 in parentheses cubed over 3. And then this is going to be 1 cubed over 3 plus 1 squared over 2 minus 0 cubed over 3 plus 0 squared over 2. So zeros are going to go away. And we're going to get +8/3 plus 1/3 plus 1/2. And so we're going to have to maybe do like least common denominator or something. I don't know. Let's see. This would be 9/3 plus 1/2, which would be 3 plus 1/2, which would be 3.5, or 7/2. Okay. So if you have piecewise, or you're looking at a graph that's made of multiple curves and you're trying to find the average value, or you're going to have to do the individual areas first to get this. Would give you your total area, and then you would divide it by the base. If we were looking for the average value from -2 to 1, we would do all this work and then get this one answer and then divide it by the base, the single base of like one big rectangle. Riemann sums we've been doing recently. And you just got to draw either Riemann sums are rectangles, okay? And you're going to either do left endpoint, right endpoint, or midpoint to determine the height of each one, and it'll change your answer. The other ones are called trapezoidal approximations, and these are not considered Riemann sums. The way you do them, so here, let's say you have a curve, and you have some values. I like to draw pictures of these. And if we're doing left, we're going to use the left side, right? And it's going to give us that. If we're doing right, then we're going to use the right side. And it's going to give us an over approximation in this picture. If we're doing midpoint, we're going to go in the middle, and they're going to give you a table of values with middles. Trapezoids, same idea. You have a curve and you have values from a table. So we always use these with tables, usually. I mean, on some of these, I'm making you do them, sort of create your own table. Trapezoids, you connect the left and right sides with a straight line, and you get these trapezoids. Now, hopefully you guys remember the area of trapezoid, and there's some crazy formula you probably try to memorize back in algebra, but to me, trapezoids are just rectangles. You can cut them up and reform them into rectangles. So the area of a trapezoid is really just base times height. The problem is there's two bases, and on our drawings for these problems, they're going to be vertical. They're sideways trapezoids. So they have two bases. So you average the bases. You add them up and divide by 2 and then multiply by the height. And that's how you get they're just rectangles. But they have two bases, so you average the bases. That's it. So I think I'm going to let you guys try these problems, and then you can look at my work online. You can check your answers. I'll put the answers up, and then you can look at the work to see what you did wrong if you made mistakes. So that's it. Finish it up.